nanohub.org.
Let me quickly tell you one thing. I will do it properly later on, but at this point, it's sort of something that you should know. The difference between a metal and semiconductor. Because somehow I missed that point. This is a energy band diagram. This is remember the EK diagram? The lowest one has a band, then the second band, the third band. I generally draw 4 of them. Okay. Now, between a semiconductor and a metal, in terms of energy band diagram, no difference. No difference. They are exactly the same. Look, they are about the same. Of course, I've drawn it shifted because this could be copper, this could be silicon. So the band might be in a slightly different place. Now, for a semiconductor, the requirement is that the Fermi level is somewhere in between. And for the metal, the requirement is that the Fermi level is inside one band. That's the only difference between semiconductor and metal. Why is it in one band? Because in metal, first of all, I kept saying this, that every band has 2 n states. Do you remember n number of atoms? 2 for the spin, 2n gives me the total number. So it's always even. If I have odd number of electrons per atom, then it's always a metal. It's always a metal. Why? If I have it odd, then surely one of my band will be half full, right? Everything is even. So if I have it odd, it must be half full. And if it is half full, Fermi level must be somewhere in one of the bands, because that is where it says below it is essentially full, above it's empty. So when it is odd number of electrons, in that case, it is a metal. When it has an even number of electrons, in that case, it can either be a semiconductor or a metal. That depends, but that is not a given statement. But generally, if the reason is many of the bands are degenerate, right? Remember light hole and heavy hole, they sometimes have the same energy. So even when you have the even number of states and even number of electrons, silicon, how many? 14 electrons, right? Even number of electrons, even number of states. In that case, it is entirely likely that at 0 temperature, a set of them below the Fermi level will be full, even and even, and set of them above the Fermi level is empty, right? And the Fermi level will be somewhere in between. That is the semiconductor. Now, the reverse statement, even number and semiconductor, is not always true because of the degeneracy I just talked about. Many times they have, but this statement is always true. Odd electrons and metal generally is true. So this is a distinction I think many people don't understand clearly. For them, metal is something completely different because the way they view it. The reason in metal you don't talk about holes is because, you see, Fermi level is here. These levels are all full. Lots of electrons moving around in copper. But this is all full essentially here. So there is no current in the valence band, quote unquote valence band in metal. So people talk about, you know, I have in a copper this many electrons, and they just never talk about holes in metal, right? They just talk about electrons. But the concepts, what you have learned this far, no distinction between metal, semiconductor, and insulator. Insulator is something that has, this is 1 eV, silicon dioxide has 9 eV. Band gap is equal, so qualitatively no difference. You see, this distinction you have to clearly understand, because many cases we'll be using this material side by side, put them together. Anytime I have a metal contact on a piece of silicon contacted like this, I have on one side this metal needle, one side this, in another side my semiconductor, the other side is this. Electron will go from here to here, here to here, and that will give rise to Schottky barriers and other things. Is this clear to you? Okay. Think about it a little bit because it's not an obvious statement. Think about it a little bit. Okay, thank you.